So I wanted to take some time to walk through the Python package GraphND, which stands for Graph, Not Documents. And the purpose of this package is to offer users a powerful end-to-end system for building agentic GraphRAG workflows with a pretty intuitive API. So the basic premise here is that we want to get people from 0 to GraphRAG in under 5 minutes, even though you might not have a lot of graph expertise. We want to build this with intent to extend to production, meaning that while it's easy to get started, it can be extended for production workflows. This also prioritizes support for loading data from multiple sources, including structured and unstructured data sources, with all of the tooling in one place. And you have, in addition to all of that, out-of-the-box GraphRAG agents. So there's a factory that lets you build agents with pre-built GraphRAG tooling installed, so everything's really easy to use, and all of that is sort of contained within inside of this one package. So I'll go ahead and walk through a quick demo of how this works. All of these notebooks are available. If you go to examples here in the documentation, you'll see there's a Quickstart, and then there's a couple others in here. The basic idea here is that we can go ahead and basically get to GraphRAG with just a few lines of code. So we're just going to walk through this block here in a second. But basically what I had to do to prep for this, I opened this Jupyter notebook environment inside of Colab. I pip installed GraphND, which is on PyPy. And then here, I'm just basically loading my Neo4j credentials and also making sure I have an OpenAI key. So this is contained right now inside of this file here, but if not, it would just get your passwords and stuff. And basically to get this, I had to set up a Neo4j Aura instance. In this case, I set up an Aura free instance here. Right now, it's empty, but fairly easy to get that set up. And then basically, I'm just going to run this code here. So I'll go ahead and just get it started. And basically what it's going to do is it's going to start everything up. I'm going to explain in plain English what I want to do. Basically the type of GraphRAG that I want to conduct. I just want a simple graph of hardware components where the components have some simple fields and some simple types. So basically this is going to be kind of like a supply chain example. The data that we're going to be using for it has to do with GPUs. So basically here I have basically this catalog. It's CPUs and GPUs actually. So it's a lot of hardware, these components. And then in addition to that unstructured data, I also have some structured data in the form of CSVs. So like here, for example, I have a CSV that explains how each component might feed into the next component, as well as different types of component types that I have here, which explains the component and then how different components might actually be of the same type. So anyway, what this does is in this first step, when I say infer schema, I'm going to infer, basically, I'm going to create a schema. The next step is going to be to merge the CSVs and merge the PDF. And then once that's done, all the data is inside of Neo4j, and I can just fire up an agent to answer a fairly complex question, like what sequence of components depend on silicon wafers. And basically, if I look at the output that it just produced while I was talking here, first I got a graph schema, which is sort of the secret sauce. I get an annotated schema that will give me all of my components and tables and stuff. It'll define my node labels. It'll define text embeddings and full text embeddings if I ask it, as well as different query patterns. That's going to be done with basically AI inference using OpenAI in this case, since that's the type of model that I'm using. But there's other examples where we can define this exact schema via JSON or whatever, so we don't have to rely on AI for that. Similarly, when I merge CSVs and PDFs, like the ones we were just looking at, it's going to use AI inference to basically do entity extraction from that component catalog. It's then going to understand how to do table mappings, again, using a preview of that, basically the top of the tables, and then understanding the graph schema and sort of how to map that over. And then you see here, I asked my question, right, with my agent, and it's able to infer that it has to do semantic search. So all these tools are sort of built in. It uses text embeddings. I say find a sequence of components that depend on, silicon wafers, which it just pulled from the semantic search. It does a path query here, and then it will give me an answer that's accurate. This is correct. That will tell me this sequence of components that depend on silicon wafers. So you see the finished logic chip and all of the sort of assembly that goes into that. And if we look at the actual query that it gave me, so I'm going to go up to where it produced this query, and I'll go ahead and just copy that. And I will go into Aura to see basically a sample of what this looks like. So match start, and then what I'm going to do here is just add p equals, and I'm going to just return the path. So you see here, this is the path that it basically got me. Where I have my silicon wafers as input, and then you see the extended path. So it did this with a text to cipher tool, essentially. And you see, though, that we were able to do all of this and get to this advanced sort of vector search plus text to cipher response with only just a few lines of code that the user had to write, right? I just described my use case, merged my data, and then I fired off an agent. And so the idea behind this, right, is that just in a couple minutes of running that, I'm already doing GraphRAG on a fairly realistic use case with some fairly realistic types of questions. And there's more down here that we can do. Like I can ask other types of questions. So for example, well, it's all the way down here at the bottom, but another thing that I should probably just mention here is that when you create agents, we can actually have these agent factories. So for example, here, this agent that I'm creating is a lane graph agent. I could also do, and I have other branches for this, where we can create, for example, ADK agents. So pretty much any agent framework that we would want to integrate with, we just go graphrag.create blah, blah, blah agent. And that could create an agent for that framework. So it's fairly easy to just add different agents from different frameworks to this. Right now, I only support LangGraph with a branch that supports Google ADK as well. But you see here, I just did that, and then I asked the same question, and it returned a similar response. And then if I were to go down here too, I can also show adding different tools. So for example, right, the great part about this is we can add any tool we want for any other database or any other web API. And then when we add that in, we can start extending our questions and getting even more information back. So, this is pretty flexible for users if they want to use Neo4j to sort of create their central kind of GraphRAG agentic workflow and then add any other federated tool to that. This makes it pretty easy to basically have that happen. And then the other things that I have in this notebook, which probably is a lot to go over in a video, so you can probably read more about it. I have in here a little bit about how the graph schema works, which is what's created under the hood. That's kind of like the secret sauce. And then I also have information on sort of how to save and reload the schema. And then let me just go here to, and a little bit of a note on how sources are tracked. So there's source IDs and source metadata nodes, so people can have some explainability into where information came from eventually. So that's the Quickstart example. But what's great about this is that you can also extend it to more, precise workflows. So we depended a lot on that in that first example on LLM inference to create our schema. But that doesn't always have to be the case. So for example, here, I have a different example with a retail source data set that has returns that are in PDFs, as well as some other tabular data that came from a database as far as what customers have purchased in the past. And in this case, right, I'll just go down to the relevant bits here. I can do an automated table mapping, and I'll get rid of this. I can do an automated table mapping here, but basically, if I do that, it will be correct. It's going to look at a lot of different CSVs. These represent all of our tables, but it's going to miss a lot of relationships. So basically, you'll see here that it knows that order details has relationships inside of it. But actually, in this case, products have relationships inside of it that link back to the original articles. Or rather, articles have relationships that link back to products, I should say. So there's other stuff in here, basically, that it ends up missing. So in these cases, we can work on our prompting to be able to get this to do better, or a user might choose instead to basically do their own. I didn't run something up here. I should probably just go ahead and do that, just so that I have GraphRAG instantiated. Then this will then work. So I'll go ahead and clear my graph. All that did was just cleared the graph out. So in case I had anything in the database, it will all be gone. But basically what a user can supply if they want their own mapping for nodes and relationships, which is really useful for going from a demo situation to a situation where you want to actually have more of a production workflow. So in this case, basically you can supply node records in this format where you supply a label and then a series of records with all of the variables that are necessarily and specified inside of the graph schema. There was some examples up above too about how basically if I was to look here where I can create schemas and I can write them back to JSON, and then I can reload them and I can edit them, etc. So it might actually be useful for me to run through what that looks like really quick before I even get into the data loading part. But basically what I'm doing here is I'm taking some other schema that I've developed in the past for this retail data set, and then I am loading it and I'm exporting it as like, hey, can I do some inference to like get a starter schema? And that starter schema, if I go to data models, looks kind of like this. And once I've serialized it to JSON, basically I can go in and make edits to it, and then eventually I could finalize on something that looks like this, right? This is the final schema that I want. I have annotations where I need them. I have different nodes as well as the different fields of those nodes. And if I went down enough as well, I would get my relationships here as well. But basically, once I have those, what it means is that I can start loading data with a validated schema. So going back to where I was before, where we were merging nodes, down here. So here, once I merge those node records, basically what will happen is it'll read, I'm reading from the CSV, I'm doing some data transformation myself, and then I'm merging nodes in. And I can go and I can actually look here, and you see I've got my order nodes that I just merged into the graph. In addition to doing that, I can also merge relationships. Relationships have their own sort of very simple JSON-like representation where I specify the relationship type, a start node, and an end node, and then I have the different properties as records for each one here. So you specify the type and then the records you want to load. So I can do that with my orders table here. I can bring in my order records and basically go customer ordered relationships. I can go ahead and run that. That will run, and then when I come back here, I should see, oh, well, now I have these ordered relationships that will give me my customers ordered different things. And it batches all of this. It makes sure that you have specific constraints and all that sort of stuff is taken care of under the hood. There's also examples here of where we can merge parallel relationships. I'm not going to go too into depth on that in the video. I have it written in text here, kind of how that works. Text embeddings as well. So In this case, I'm doing with this product PD or CSV rather. I want to create a text field, which I do here. You can see I create this text field, which name, type, category, description, and within inside of our graph schema, that has an embedding associated with it. So if I went to my graph schema here, and I looked for product. No, I want product in here. Control F. No, you're not going to do that. But I could probably just scroll to find it here. So here it is. Here is the, well, this is the credit note. And then here is the product. So here you can see the product node. And then the product node has some properties, and then it has what we call search fields. Search fields will specify that there's a text embedding on the text field. And so basically, if I X out of that really quick, what that means is that when I go back to my text embedding here, and I do the load where I just say, hey, merge nodes, I don't, as a user, have to do any vector index creation. I don't have to specify really very much. In the beginning, I already instantiated GraphRAG with my embedder. So all I have to do is say, hey, merge these nodes. And as it does, this will take a minute because basically what's happening is as we're loading in, we're going to make batch requests to our embedder. Which is in this case going to be OpenAI text embedding ADA02, and it will create text embeddings as it loads data in. And while that's going, there's other nodes and relationships that we need to merge here, so I'll go ahead and just start running all of those suppliers and all that sort of stuff. So those will all be getting run after this one finishes. But we can probably take a look pretty shortly here as far as what that will look like, that schema will look like. So now we're completing. All right, so all of those just completed. And now if I go back here, you'll see I have many more node types. If I look at the product node type, you'll see here I have my description, I have my text, and then I have my text embedding as well on all of these, which is great. And I can look at my schema that I created. And you can see here I have, I'm going to make that bigger. I have my articles, which are specific instances of products. These products have a product type, as well as being part of a product category. Customers are down here, and customers make orders, and those orders contain products. Or contain articles rather, which are supplied by different suppliers. That's basically this graph in a nutshell so far. Once I'm done with that, I can also do text extraction using the same exact tool. With GraphND, everything's sort of bundled in the same place so that you don't have to go and use a bunch of tools in disparate places. And what I'm going to do here is I'm going to say, hey, I'm going to get this credit notes PDF. Which is basically this PDF of returns. And I'm going to specify a sub schema. So I'm basically going to say, hey, for this PDF, all you're going to do is basically take patterns of credit note, refund for order, and credit note, refund of article. And this is going to validate that these patterns exist inside of the schema. And then it's basically going to tell a LangChain workflow, hey, go ahead and extract nodes and relationships of these types from the documents. And this is all running async under the hood. so users don't have to worry about different async commands when they're running between notebooks and just normal Python scripts and other code. And so this will take just a little bit of time because I think there's about 300 pages inside of this document. If we were to look at the document itself, we'll go down to sample data. This is the wrong sample data. We want data. And we go to the credit notes PDF. And we can see here it's 308 pages of basically these return notes to customers. And you can see it has the credit note ID, the product stuff, and it will merge all of these in. In fact, it will merge them in an idempotent way, which is super important for unstructured ingest, to have an ID that gets resolved and then gets merged in automatically. We're almost done. This might be throttling on my OpenAI key just a little bit. Sometimes I wonder if they slow down API calls if you call it too frequently. Or maybe not. We'll see here in a second. Alrighty, so we merged our nodes and relationships. So now if we go to our schema here, what we'll see is we added this credit note and the refunds, which go between the orders and the articles. And what's interesting about this, I didn't show you the counts before, but basically it joined back to the correct article nodes here. It was able to extract IDs. The graph schema will specify that every article has a required ID field. In this case, that ID field is, I think, just article ID. If I were to look at one, yeah, article ID. And so the articles that have returns, if I probably just go for a credit note, and then expand out on a credit note, you'll see it just merged back to existing articles that were inside of the database. So that's why I was talking about that sort of idempotent ingest. If I run this again, it shouldn't create any more nodes or relationships. It should just merge everything in the same way. And then from there, I have examples here of running the GraphRAG agent where I can ask questions like which suppliers were responsible for the most refunds. And I can go ahead and just run this again. But basically it should do an aggregation query here. You'll see it'll go ahead and run credit note, refund of article supplied by supplier. And then it will just do a count on the supplier name, and it will give me, in the end, a little table or a list here. But I can also add custom tools, which is, again, really important for when you think about productionizing workflows. So I can go here. I can add get product recommendations with some custom cipher that uses almost like a collaborative filter join. I can get different summaries of orders and suppliers here using my own logic to sort of understand number of orders refunded and whatnot, and sort of looking at the inverse of that either through the product or the supplier view. So just go ahead and run that again. And then when I create my React agent, I can go ahead and create it with those tools. And then basically what that means is now I can say, what are some good sweaters for spring, right? And then it should, in this case, use, this will just use a normal node search. But what will happen is this isn't a specialized tool. This is just part of GraphND. If I said, what else could you recommend to go with that? What it will do now is it'll now use this get product recommendations tool with the article ID. So that's my own specialized tool. And it will do this sort of collaborative filtering search in the graph to be able to return a response to that. Same if I ask which suppliers have the highest number of returns, it should go ahead and at least attempt to use. So we'll start with an aggregation query here, and that will be what it will run for that. But if I step that up a little bit and I said, what are the top 3 most returned products for this specific supplier, and to get the product codes, we'll see here that it will use the specialized tools of get supplier order info, get product order supplier info. So it will start to use these specialized tools that I have to be able to return an answer, basically using Cypher that I've pre-approved. I have another section down here to go over MCP integration. That's super easy. It depends on what the syntax of it will depend basically on the agent framework that you use. But for LangChain, you'll see here, it's basically you just define tools like this, where I just get the tools from an MCP client. And with ADK, you basically have a similar type of notation where you just add tools from a different type of MCP object that you declare with some pointers to your server or whatever you're using for that. So that's all fairly easy. The last example that I have is just to show that GraphND can also be used with pre-existing graphs. So this is a graph that we have in labs that represents different companies and articles written about them. It's a sample of diffbot's data. And if I go ahead and run this, run anyway, install GraphND, basically connect to this public database, what I can do is I can instantiate my GraphRAG object just like before. I give it a Neo4j client, a language model, and an embedding model. And then what it will do from there is, once this completes, so now I've installed. Alrighty, I've tested my connection. I'll go ahead down here and instantiate my GraphRAG object. And I need to get my OpenAI API key, which I will do here. Alrighty. And I can basically have 2 lines of code to get a schema. It'll give me a lot of warnings because basically when I instantiate a schema from another database, it might not make the same assumptions necessarily that GraphRAG makes to offer sort of that really nice experience where the user doesn't have to do anything. For example, there'll be different ways that people basically will lack constraints on different nodes. So it'll create warnings when it can't find the constraints that it wants for different node labels. And then in this case, for example, right, like it, if I look here, you know, for the city node, the country nodes, and the chunk nodes, there was no like node ID with a constraint on them. So it sort of fell back to choosing different properties in there to use as an ID. As a fallback. Every node has to have an ID. So this is all explained inside of this notebook, kind of what assumptions are being made. But from there, right, I can go ahead and just do, you know, it made an error there before, but because it's an agent, it's able to go, oh, okay, I'm going to fix that. So it used a full text search here. Basically, keeps trying. Here we go. and it will find some articles that mention GPU. So it'll do a full text search here with this search config, and it should say the search query in this case was just on GPUs, and then it brought back that search query for full text search. And then if I ask a question like this, how many people exist who have been both a board member and a CEO at some point, even of separate organizations, it'll attempt likely to do an aggregation query. And you even see the instructions that it gives for the downstream LLM to create an aggregation. While that's running, oh, you see there it came back. So it looked for a person who is a CEO, and then a person who is also a board member of some other organization, and then count distinct, and it got 410 people. So it went ahead and just used text cipher to answer that question. And then there's a ton of stuff down here where we talk about, hey, you can add text embeddings. Because of the way Neo4j works, you actually need to specify a mapping between the vector index and the field that it is embedding. Then it can start to use text embeddings for semantic search. There's a lot of details that I have here on the assumptions that are made with graph schema, and using just sort of any arbitrary Neo4j graph database, which you can do. It generally won't error out. It'll just throw warnings if it can't find exactly what it needs. Alrighty, so that's it. That's GraphND in a nutshell. Hope that was helpful.